Good morning, everybody. How are you today? Yeah. What about the weather? Yeah, it's great. Sunny outside. Yes. And what about the life in the campus and everything's doing well? Yeah. Okay. Great. So let's start. We today we will talk about the a very fundamental and important concepts, the neutron flux and the neutron cross section and neutron reaction rate at the related between these two, the reaction rate, and how this reaction rate, as much as it's fundamental, but as much it is very important to drive the nuclear reactor, and also if it's responsible for the nuclear accidents, so that we have to understand these parts very well. So somebody, do you remember this picture? Yeah, it's Chernobyl disaster. Yeah, it's 26 April 2000, no, I'm sorry, 1986. Anybody was there at this point? I think most of you is born after these dates. I was there. So I remember it was a big disaster, and this changed the face of the nuclear industry and delayed the nuclear industry all over the world for years, and until we understand the problem was in the design of the reactor itself. But why this nuclear disaster especially happened? Okay, because there is a heat increase in a specific part of the core due to the lack of the design, and due to the lack of experience of the people in this night, so that the heat increase inside the core. So what is the source of the heat increase? Yeah, for the chemistry was the source. When the heat increase in the electricity, what? Because the reaction rate increase. The similarly for this one, the reaction rate of the neutron with the fuels increase inside the core, that drive the reactor to catch the fire and causes a big disaster. Now, if we look at the what is a factor, what some main factor or fundamental factors that control the energy produced in the reactor. Okay, this is a schematic of reactor schematic diagram. You have been seeing this before, and we talk about the parts before. Where is the core? Yes, this is the core of the reactor. Okay, so if we look at this the fuel here, the reaction rate increase, the heat produced from the reactor increase, and as much as the energy increase. But this reaction rate should be under control by using, yes, control rods. And this power reactor, this is an experimental or pool reactor. This reactor, what do you remember? Can anybody remind me about why the blue right here? The blue rays, yes, the blue rays, because of the electric charge, which is delayed, okay, or decelerated by the water, which is Cherenkov radiation, definitely. But all of this we now what do you have to learn today? Okay, what you have to retain in your mind and keep it for as much as possible. Okay, because you will apply this in the future. You have to know by the end of the day what the meaning of the reaction rate and why it is important, and the concept of the flux is the flux and why it is important to calculate the reaction rate. What is the relation between flux and reaction rate, and also the relation between the reaction rate and energy produced and production rate. So but in order to know that, we have to know what is the meaning of the cross section and what is the meaning of flux. So we need to understand what is the interrelations correlate between these physical quantities, and understand how it affects on the reaction rate. So we'll start our lecture with explain the concept of flux, and then the idea of neutron cross section. And you have to know the units of each quantities, like microscopic cross section, the flux, what the unit is, and the idea of the group flux, what the meaning of the group flux, and finally how this group flux can be affect on the reaction rate. And we will see some problems for that. Now, what is a flux? The flux, if you imagine those troop soldiers, and you see this is 8 lines, okay, and those people, suppose that they are driving, they are moving this direction, okay, and you would like to hit this wall, okay, break down this wall. So the number of those people, okay, which is not 8 lines, okay, if hitting the walls, it's 8 per unit area of the wall, Okay, but if we make them very close to each other, or too closer to each other, that's mean the number per unit area will increase or decrease? Yes, will increase. That's mean the force on the wall will increase. Okay, I can explain that for something to the similar to the neutrons. If those just walking with a small speed or walking with a higher speed, which case will affect more in the wall? Yes, the higher speed. So that therefore the flux is similar to this same idea. But in the case of the neutron flux, you will find the difference because the neutron flux definitely has a specific direction. You will see that later. So that suppose that you have an n number of neutrons, and this n number of neutrons traveling in different directions and traveling from different directions and falling on the per unit area. So the number of neutron per unit volume which is n per meter cube, and they travel with a velocity v meter per second. Therefore the flux is multiplied both of them, the number of neutron and velocity, because both of them are affected on the target. The velocity, because the velocity related to what? Yes, related to the energy, where E equal mv square. Okay, now what's the unit of the flux? You know, n is a number, has no unit, and this is meter per second square. Okay, but if we talk about the number of neutron per second, that's mean we have to divide by second. Therefore, the unit of flux is n, which is just number meters per meter square second. Sometimes we can say the flux is the influence or the fluence rate. Okay, do you hear the word before the flux? Yes. You heard the word flux before, not the stomach flux. Yeah, the flux of the magnetic flux. But what the magnetic flux has a specific direction, the number of magnetic lines passing through a unit area. But in this case, we will see the flux has no direction because the neutrons coming inside the reactor from different direction in all directions. That's why we can represent this flux is a scalar flux, not as a directional flux or vector flux. So in order to understand also the neutron, therefore the neutrons coming from different directions interact with the fissile nuclei of the uranium-235. So what from this point, what is a factor that affect of the probability of interaction between neutrons and a target nuclei? Yes, the speed of neutron, okay, and the number of neutrons, which both of them represent as a flux, the speed that is between energy and number of neutrons, and also the type of nuclei. Because if this nuclei is uranium, there is a fission reaction will maybe happen, and if it's aluminum, there is no fission reaction. That means also the type of nuclei. We need to put these two concepts together in one meaning. Okay, so in one meaning is a cross section, okay, which is represented as the probability of interaction. That means this probability of interaction depend on the energy of the neutrons, and in the same time depend on the type of nuclei. And the type of nuclei, we make it simply here is a cross-section area of nuclei, which is around 10 power negative 24 centimeter square or 10 power negative 28 meter square. And this unit called a bar. So that the cross-section or the microscopic cross-sections represent as a probability of reaction occur between one neutron and a nucleus is measured in terms of the effective target area. And this effective target area is 10 power negative 24 centimeter square, and this is called barn. So that when you see the word barn, that's mean it is one, you have to convert it to centimeter square. You have to multiply by 10 power negative 24 or meter square times 10 power negative 20. Yeah. Now, what do you think about the neutron flux inside the reactor? Is it to have one energy, two energy, or a spectrum of energies? Yes, a spectrum of energies. So that in order to understand how this energy or neutrons interact with the target nuclei inside the reactor, we have to discretize this energy into energy groups, this flux into flux energy group, so that or flux groups, so that the flux group is integration of a specific energy, or at specific energy is a limited integration between two energies, E1 and E2, two limits of the flux as shown in this figure, if you would like to talk about the flux of these two limits. Now, and also this is also correlated to the cross section, because the cross section section is at this limit is different than between the cross section of the other limits, so that these two limits is correlated to the cross section or the probability of interaction of this specific group with this specific type of nuclei. Now, in general, we can classify the energy between of the neutrons between thermal, which is less than 0.24, and this is epithermal range, okay, 0.04 electron volt until 1 keV, and the intermediate between from 1 keV to less than 500 keV, and the fast, which is, or the high energy neutrons between 500 keV to 10 MeV. And you maybe find this is a classification different from one book to another according to application, but it is clearly in our work in the candle reactor, we use a thermal energy, the thermal neutron energy, which has an energy less than 0.625 electron volt, and the other group, okay, all the group, I can say high energy, but all the other group is has an energy greater than 0.625. I can say this is a first group energy and the second group energy, so that in candle reactor we use two groups, and this is two limits of the two groups. Now we came to the main important point in our lecture today, which is the reaction rate. In order to understand the meaning of the reaction rate, we have to do some simple mathematics, and but in the general, the reaction rate is a number of the interaction takes place inside a target, or inside the bulk of elements or of target nuclei. So suppose that we have this delta X slab of thickness delta X, and this is a target nuclei, and this is a neutron's beam fall on it. So the effective target area of the present is represented as a number of number density, which is the number of nuclei here, multiplied by the thickness, okay, multiplied by the area, that means this is the volume of this one, times the probability of interaction, which is represented as the cross section. Okay, so this represents as the effective target, not the volume of the target or number of the effective number of nuclei. If we keep we drop sigma, that give you the number of nuclei, whole number of nuclei here, but that's this beam will not interact with all number of nuclei. That's why we put this sigma here, that's to give us the sense of the probability of interaction with this target. If we multiply this probability of interaction with this target with the flux, which is represented as a number of neutrons per unit area, number of neutrons passing through per unit area in 1 second, so that this give you the reaction rate. The reaction rate is then equal to the n number density times phi, the flux, times sigma, which is a microscopic cross section of the nuclei here, times the area of the slab, times dx, which is the thickness of the slab. Area times dx represent as a volume, therefore this give you the reaction rate. The sense of reaction rate here, it depends on the number density, number of nuclei per unit volume of the target. It depends also on the flux coming to the target, number of neutron per centimeter square per second, and depend also the probability of interaction of this neutron at certain energy with this target, and the volume of the target, okay, at all. So that give you the sense of the reaction rate. So simply anybody can deduct the units from the units balance. Therefore the units is of the reaction density, reaction rate is a number of reaction per meter cube or per unit volume per second, because its rate should be per second, and it should be controlled by per unit volume. Okay, so in this case, now let us see this problem and try to solve it. Okay, you have a reactor, you have 100 ton of uranium in the said reactor, just only 2% enrichment, uranium-235. That means this only amount will interact with the neutrons at the fissile isotope, and it's a fresh. You have to differentiate between this is enrichment and the fissile. In the fresh fuel, the fresh fuel is 0.7%, this is 2%, so that you have a thermal neutron, and you need to determine what is the reaction rate. Just use this information to calculate it. Okay, I will expose it at the end of the results after a few minutes. So you have now this information. You have to know what the definition of the flux okay, and what the microscopic cross section, and what the unit of each of one. Why do we classify the flux into energy groups? Yes, in order to each group interact differently with the target nuclei, and define the reaction rate you have, and define the factors affecting it, or the factors affecting the reaction rate, the flux, the number density, and cross-section area. Is it impossible? It is significant to classify the flux into groups, and why? You have to you have to know the answer to these questions clearly after this lecture. Thank you very much, and have a good day.